everyone here working with categories? Everyone here liking categories? Or is there someone that doesn't like them or do not see them in their research?
Second question is a little bit more problematic.
Okay, I see. So, because I can imagine there are people out there a little bit afraid of categories. So the first thing that I wanted to address is that, but it depends if it's meaningful to do that.
I think that's a better mix.
Okay, so I will do my best in this talk to basically argue that here categories are what you really need to formalize what you have in your mind. So it's not going to be like we want to use categories because we like them so much. It's more about trying to say something meaningful, and so we need categories for that. Now, this presentation is going to be divided in three parts. The first part is preliminaries and motivation. So we will see why I'm interested in discussing abstract measurable spaces and non-commutative side of it. Then we will consider the so-called deterministic side, meaning the side with homomorphisms and the maps that are preserving the multiplication, for instance, for the algebraic side. And then we will move to the probabilistic side, which for people in operator algebra will be completely positive unital maps. And we will see how these are really like the probabilistic side also for the commutative case. So the main motivation is basically, I would like to find a setting or a category where I can consider both classical and quantum probability at the same time, and it has to have some nice properties for working on this setting. So generally in classical probability, what we consider is measurable spaces, and then we have like this sigma algebra associated to a set X, which is basically like a family that allows you to write integrals, I would say. And generally, measurable spaces are like a very wide family, so you don't want to consider all of them. And for many reasons, people generally restrict to standard world spaces, which are measurably isomorphic to finite sets, the integers with the power set, and the real numbers with the Borel sets. And these are generally like the spaces someone working in probability theory will restrict to. Instead, in quantum probability, generally one considers unital σ-algebras or σ-algebras, or also von Neumann algebras. I will discuss them briefly. But yeah, so it's all a little bit related to σ-algebras. At least if someone doesn't fight me on that. And then we also have another side of the story, which I wanted to add for this talk, which is the use of lattices to discuss quantum logic, because projections there are the most important definition. Okay, so far so good, I hope. Okay. So I wanted to give you like an idea of what σ-algebras are, at least in my mind. So if you already know what σ-algebras are, this will be boring maybe, but the idea is that a Hilbert space is basically giving you a quantum system, and then when you want to consider observables over the quantum system, you generally consider bounded linear maps. Of course, not everyone will agree with this. There are a lot of things doing with unbounded operators, but here for us, we will only consider bounded operators. And then a σ-algebra is basically, first of all, an algebra over the complex numbers inside the bounded operators over a Hilbert space. It has to be norm complete, where I take the norm from the operators. And then star closed, which this star is the adjunction property that I have on Hilbert spaces, on boundary operators of Hilbert spaces. I will give you examples after this slide, so don't worry if you don't get everything. And then also unitality, which is not always considered. For example, there is like a lot of study on compact operators, and those do not have a unit. So that's like a big example to consider also stuff that is not unital. But for us, every sister algebra will be considered unital. And one really important thing is the fact that I can define a positive cone when I consider a sister algebra, which is basically given by this definition, which may be a little bit hard to digest at first, but it's really good to see what this really means in examples. And so let me discuss this with examples. So if I take an algebra, a matrix algebra, like MN, then I get that the adjunction, the adjoint is given by conjugating the whole matrix and then taking the transpose. And an element is going to be positive if it is a positive semi-definite matrix. Another very important example is given by compact Hausdorff spaces. And now here I can consider just continuous maps from X to C. And this is going to be a sister algebra. And now we see that the transpose doesn't play a role because it doesn't make any sense here. So we just conjugate the thing. And now a positive element is just going to be a non-negative valued element. Okay. And now this example is like a very broad class of examples. So broad, in fact, that it comprises all commutative unital sister algebras. And this is what's known as the Gelfand duality. So on one side, I have compact Hausdorff spaces and continuous maps. And on the other side, I have commutative sister algebras and star homomorphisms. Okay. Just reminding you, star homomorphisms here are really preserving the multiplication, the addition, linearity, and the star operation. And this gives you for free that it also is bounded. That's like non-trivial. Okay. Now, what I want to study though is how this behaves for probability. So instead of considering star homomorphisms, one would like to consider CPU maps, so completely positive unital maps. Just to give you an idea of why that would be probabilistic in some sense, is the idea that a probability measure on P on a measurable space requires two things, which are complete positivity, which is basically to say that it's going to be positive, and then it's going to be unital as well. So these are the two things. Then, of course, this is not the definition of a probability measure. You have the other thing, the sigma additivity, that you should not forget. But for the sake of this slide, this is what I want you to think about, and the reason why you have complete positivity on one side, which is like it's positive and it's behaving well with considering many systems together, and then it's unital because you want the probability to be normalized. And now we have also like a very nice result, which is Ritz Markov-Kakutani theorem, which tells you that CPU maps from C of X to C as sister algebras is actually in bijection with random probability measures on X. So this is kind of telling you that possibly sister algebras are a good non-commutative version of probability theory as well, and one could consider CPU maps. And in fact, this can be formalized to this to get this theorem, which is the probabilistic Gelfand duality. So on one side, you have commutative sister algebras and CPU maps, and on the other side, you have compact Hausdorff spaces and continuous Markov kernels. So first of all, what are continuous Markov kernels? Well, a Markov kernel is the generalization of probability of a probability measure, but now with parameters. So to every element, you associate a probability measure on the target. Every element of the source, you get probability measure on the target. And it has to satisfy some conditions of measurability, because then you want to use integrals again. So that's the only thing that you need to force for Markov kernels. And now continuity is a subtle property, because although we call them continuous, they are generally like lower semi-continuous. So it's not like a very nice property. But nonetheless, we have a connection between the non-commutative side and the commutative side. So this seems to be like the end of the story. But I'm here today, so it's not. And the reason why is that continuous Markov kernels are not ideal for probabilistic studies, because you don't get conditionals. And this is a huge problem, at least if you try to understand conditioning from a categorical viewpoint. So you would like to see them in the category and not going outside. So this class of regular conditionals are, we can prove that they are Markov kernels, but the continuity is blocking us. So what should we do instead? Well, yeah, so this tells us that commutative σ-algebras are not good for probability, because I would say every sensible probability theory should have conditionals, because that's like a very important tool for probability. Maybe people will fight me also for this statement, but I do believe in it.
You just say that random probability measures are not good for probability.
Oh no, well, those will still be the right measures, but then you also want to disintegrate that measure. And then if you want to disintegrate the measure, then you should consider something more. But in fact, random probability measures are still going to be the only measures that you care about. The problem is not the measures, it's rather what are parametric measures, so those Markov kernels that you allow. Okay, so now I want to give you the motivation in a more concrete manner. I want to have an equivalence between the category of standard Borel spaces and Markov kernels, the right ones to get conditionals, and a category of special commutative σ-algebras. Using this idea here, what it means is that at some point I will be able to drop this commutativity request, and I will get something that is a little bit more suited for quantum probability. Of course, there is another way of thinking about this issue. So to me, the classical side is a little bit more settled in a sense, and I believe that standard Borel spaces are a good setting for probability. But of course, we can swap around the story and look at it from quantum probability and say, well, in quantum probability, we really want von Neumann algebras. And then what do von Neumann algebras correspond to? This has been already discussed by a paper by Pavlov that you can see below in the footnote. And the problem is you don't get measurable spaces, you get this notion of enhanced measurable spaces. For example, you don't get the real line with the Borel sets, but you get the real line with Borel sets and the Lebesgue null sets. And you need to consider the Lebesgue null sets. And the idea is basically that you always don't care about null sets, and you need to keep track of that. Which, there are some subtleties to this, and I have many motivations not to believe in this direction, but of course it's still like a viable idea to proceed on. But for the moment, I think it's good to just signal that there is another possibility and go on with the presentation, unless you're interested in exploring this. I guess not. And also there is the other side of the discussion, which is quantum logic. So in quantum logic, I would say that it is common to consider ortholattices. And generally, these are given by projections of sister algebras, generally meaning like what you want to consider maybe, but of course, like there are many that are not coming from a sister algebra. I'm not trying to say that. The only problem is that if I take a general sister algebra, I do not get a lattice. I get something bad. So then the generality of sister algebras is not really ideal for quantum logic, and I should consider something else, which generally is for Neumann algebras. And then I take the lattice, and that's like a complete lattice. Everything works nicely. Here instead, I will give you a different approach to this, which will not move to von Neumann algebras, but in fact, it will basically move a little bit to that setting without committing too much, so to say.
Also, like sister alphas have very few projections.
Yes, exactly. That's the point. Like you don't get a lattice because you have very few projections. And whenever you have projections, it's also not really clear if you have a minimum, if you have a maximum. It's really not working because you don't have enough structure basically to force that to be the case. Okay, so this concludes the motivation and the preliminaries. If you have questions, doubts, or anything, no, okay. So now let's talk about the deterministic side, or maybe I should say like the homomorphism side, or many other names. Yeah, because deterministic could be a little bit misleading for some people. But yeah, we decided to go to this anyway because for the classical setting, it makes sense. So now, how do we get this equivalence that would be the main goal? First of all, we would like to understand how to associate a sister algebra to a measurable space. And the idea is pretty simple. You take a measurable state, a measurable space, and you associate the algebra given by bounded measurable functions, complex values measurable functions. This turns out really to be a sister algebra. But we already have a problem. Like if I take the set of two elements and I just take the power set as a sigma algebra, or I take the real numbers and then I just consider the sigma algebra given by one proper non-empty subset. Well, how do I distinguish the two? You cannot really distinguish the two. And in fact, the two algebras associated are going to be isomorphic. So we don't get an equivalence, but maybe we get something similar to an equivalence, a little bit weaker, which is really appreciated by category theorists, which is an adjunction maybe. Okay, so we will see how we will get an adjunction, or like that we will get an adjunction. But before that, I want to stop a little bit and say, what is the additional properties that is satisfied by this particular sister algebra that wasn't satisfied by C of X, for example, so the continuous functions. And it turns out that the idea is that we have the sigma sister algebras, which is a sister algebra. And also we have this long property, which is basically telling us that we have like countable type of limits, which we could simply say we have pointwise limits, just to simplify it. This has been already around, and it's been defined in this book, Monotone Complete Sister Algebras and Generic Dynamics. It's important to point out here that sigma complete sister algebras are considered, but they're not really the topic of the book. They really care about monotone complete sister algebras. And These are like a bigger class where also phenomena algebras are considered.
We have two kinds of limits, because now we have the limits in the C-star algebra from the convergence part, and then here you have the limit from the order theoretic part. And
yes.
two coincide, right? Or not?
Not really. It's a little bit subtle. One is uniform. So like the classical thing with the norm. So for C-star algebras, you get uniform limits. This one instead are like pointwise limits. So there is like a strong connection between the two, of course, but it's not really like every time. I think every time you have a limit in the order sense. No, you have a limit in the uniform sense. You can find something like a subsequence that gives you the pointwise limit, something like this. Because there's also like noncommutativity giving you a headache in the middle of the things. But yeah, there is like the obvious direction, so to say, kind of works, and the other one will not necessarily work. So now, just to give you an example, I will give you an example that is also a von Neumann algebra or a W-star algebra, and it's possibly the most famous one, maybe with the reals instead of the unit interval. But instead of considering bounded measurable functions, you now consider Lebesgue-Mosher classes of bounded measurable functions, and this is in fact a commutative sigma C-star algebra. And it can be proven that it is not isomorphic to any of the sigma C-star algebras that we just defined. And the idea is that this thing doesn't see points, because every point is going to be a null set. So you don't see points, but you see like the behavior in general. So that's the reason why it's not going to be isomorphic. Nonetheless, we still have a duality, an adjunction duality. So on one side, we have measurable functions, measurable spaces and measurable functions. On the other side, commutative sigma C-star algebras and sigma homomorphisms. And this has been like the first theorem of our paper. Now, also, yeah, I forgot to say that, like, sigma homomorphisms are star homomorphisms that also preserve the pointwise limits. So the supreme of bounded monotone increase in sequences. Okay. Should I say? Yeah, as we already saw, this is not an equivalence, right? Because we have, I showed you two situations, two measurable spaces that lead to the same Okay. Sorry about that. Appears my computer decided not to be connected to the Wi-Fi anymore. Oh, where was I? Okay. So, okay. Okay, so I was talking about Boolean sigma algebras. We have the classical sigma algebras coming from measurable spaces, but we also have other things that are not going to be associated to a sigma algebra. For example, we have quotients. And here I quotient with the meager sets, the ideal of meager sets, or the ideal of Lebesgue null sets. So these are two things that one could consider. And in that case, they're not going to be sigma algebras. So it's a little bit more general and it allows to consider more things. And in fact, we can still construct from a Boolean sigma algebra an abstract version of the construction that I showed before for measurable spaces. So instead, we now consider maps from the Borel sigma algebra associated to C to the Boolean sigma algebra, and I consider bounded sigma homomorphisms, where bounded is basically saying that there is a bounded set inside the sigma algebra that goes to true, to the value true. And this is proven to be a sigma sister algebra. And the idea here is basically that I have like a way to reverse maps. So then the maps from BC to B are playing the role of the thing that goes on the other side. If you think about how you will consider this at the level of sigma sister algebras, this is quite clear, because what's a measurable function is just a function whose preimage is going to send the sigma algebra to the sigma algebra of the target to the sigma algebra of the source. So that's the reason why the direction is swapped there. And we also have this nice thing, which is the classical von Neumann algebras, von Neumann algebra that I defined in the previous slide, is now simply seen with this abstract construction by taking the quotient of the null sets of the Lebesgue measure. So basically, it doesn't matter if you quotient the Boolean sigma algebra or if you quotient the sigma sister algebra. They will lead anyway to the same thing. Okay. And now we actually get an equivalence between Boolean sigma algebras and sigma homomorphisms, and commutative sigma sister algebras and sigma homomorphisms. So the two things are equivalent, and on this side, I just take the lattice of projections. In particular, this also holds. So like the L infinity of any measurable space is just going to be the abstract L infinity of the sigma algebra associated, which is also what happened with the example with the two element sets and the real line with just one proper non-empty set. So, okay. Now, if I compose this result with the other result that led me to an adjunction with measurable set, I actually get an adjunction between Boolean sigma algebras and measurable spaces. This has already been noted and proved in this paper by Ruiwen Chen, who had similar ideas, at least for the commutative side, in the sense that he also wanted to study standard Borel spaces and try to describe them. Okay, so far so good. Now I would like to, of course, go back to my main goal, which would be to kind of like restrict the setting as to not consider just measurable spaces, but measurable spaces that behave well, and in which I would hope to find conditionals. So can we find an equivalence with measurable spaces? And the answer is yes. And to do that, we basically consider these envelopes, which is also like people categorically oriented may see this as like a description of an adjunction. But anyway, for any sister algebra, we can find a sigma sister algebra associated to it that basically transfer every homomorphism to a sigma sister algebra to a sigma homomorphism. And this is known as Feddersen-Bear envelopes. Yes, this leads to a functor from sister algebras to sigma sister algebras, which is left adjoint the forgetful functor. Although this doesn't really matter if you don't know what it means. But the thing is, these sigma sister algebras really are well behaved. And first of all, we have a discussion about the classical side and why that is well behaved. And the reason is this connection with Baire measurability. So like for every compact Hausdorff space, I basically can find a sigma algebra associated to a compact Hausdorff space so that I get this isomorphism. And this is not the Borel sigma algebra, but the Baire sigma algebra. And Baire measurability has been studied like in the last 10 years, I think, for uncountable probability. I will discuss this shortly. There will appear something in the footnote side, but in any case, we get the restriction, which is exactly an equivalence as we wanted. So we have Baire measurable spaces and measurable functions on one side, and commutative Feddersen-Bear envelopes and sigma homomorphisms on the other. Yeah, I like doing spoilers, I guess, but this has been studied as like a good framework for uncountable probability, and this is possibly the most important paper by Asghar Janmashan and Terence Tao, but they also wrote at least another one, and they showed how you can generalize theorems outside of the countable or separable constraint. So this already shows that this description is possibly giving the right definitions, at least for the commutative side of the story. But the structure that you get on Feddersen-Bear envelopes in general is also quite instructive, and it tells you a lot, and you can gain a lot of information from, and you can take some things that hold for sister algebras, which do not really hold for sigma sister algebras, but for Feddersen-Bear envelopes, they hold. So it's a good candidate for quantum probability as well. Another important thing is that we can also say, we can also talk about standard Borel spaces. So the idea is that if I have some countability, then a compact Hausdorff space becomes a Polish space. So I can associate to it a standard Borel space. And second countability is the same thing as asking the sister algebra to be separable. So now I can simply say that standard Borel spaces are going to be contravariantly equivalent to commutative Feddersen-Bear envelopes of separable sister algebras. And also, thanks to this paper that I cited before, Universal Characterization of Standard Borel Spaces, I get that these are contravariantly equivalent to countably represented Boolean sigma algebras. Overall, this is what we saw. So I like this nice picture. I guess if you're scared of categories, you don't. But the idea is exactly like summarizing what we saw. So we saw that measurable spaces have an adjunction with commutative sigma sister algebras. These are equivalent to Boolean sigma algebras. This op means that it's like a contravariant adjunction, so to say. So op will stay here. Okay. Then I have like inclusions of this subclasses of sigma sister algebras, of Boolean sigma algebras in Boolean sigma algebras, and then of measurable spaces. and I get equivalences and equivalences. While I was presenting this to another university, someone asked like, why there is nothing here at this level? And the problem is, I don't know yet if I can describe the whole generality of Peterson-Bear envelopes just using sigma algebras. There is like a silly way, but I would like basically to find a non-silly way to describe that category if there is one. So that's why it's at the moment been omitted.
Is countably presentable notion the same then, or in the same spirit than locally presentable categories, one that you are considering?
So countably presented here means, well, I guess the same that will mean for Liouville theories. But so yeah, you have like countable generators and countable relations.
So perhaps a thing to do is to study the presentability of the category of Boolean sigma algebra science. So for instance, so there is this book by Giry and by Hosiki on representable categories.
Yeah.
I guess you know it, right?
Partially, yes.
Okay, one thing they do is they study categories of algebras in terms of presentability, basically saying that most of them are finitely presentable or countably presentable. And in this case, when you have a category which is countably presentable, that means basically that the category of or subcategory of countably presentable objects, which is what you have downstairs, is a dense subcategory of the category upstairs.
Yeah. I've been asked if I think this is dense, and I don't know the answer to that.
That's my question.
Okay. Yeah, I don't know at the moment. I don't know the answer to that, but it would be interesting to know if there is like a way. Although I am a little bit skeptical based on how much better behaved this category is with respect to this one, but you never know.
That's why I'm recommending that book, because they have lots of techniques for you to check whether it is dense or not.
Yeah. Okay. Thanks. Okay. Other questions?
Maybe related to that, is the the very top left. There's a monad.
This one?
Yes, that's the
monad.
This is not the Jury monad.
No. On the category of measurable spaces, you have
The Jury monad. Yes.
And I was also wondering if you can transport using the adjunction, this monadic structure to the other end.
Yeah.
Use some kind of comonad, I guess.
I think.
I just need to check whether the composition.
I mean, there's a much more direct way to see that. But if you want to use abstract nonsense, I think you can do it, and it would be safe to do. This is an idempotent adjunction, by the way. So like, it's really the nicest adjunction ever. So I do believe it will be okay. Also, if you take a measurable space and you go back, I think like Markov kernels cannot detect the difference between the two. That's another important thing. This paper by Sean Moss and Paulo Perrone, where they discuss also like sober measurable spaces, and basically like this adjunction sends a measurable space to its sobriety, and the two things cannot be distinguished by Markov kernels. So that's also another thing to consider. So on the other side, you would also get something similar. Okay. I also decided to highlight this other part to tell you like this is the general story, but these are the nice settings for probability theory, and this is the most used one, the standard world spaces, just to keep things in line with the vision of the whole project. Okay. Other questions, comments doubts, references. So then we have the probabilistic side of the problem. So we want to consider CPU maps. Instead, I want to refresh your knowledge of probability measures. So a probability measure on a Boolean sigma algebra is basically defined exactly as you would expect for a sigma algebra or like a measurable space. So I ask for positivity, normalization, and then sigma additivity. So for a countable sequence of pairwise disjoint elements, I can write this thing. Okay. And the reason why I am writing this is that, for example, this thing is a little bit ill-behaved if we want to consider it for σ-algebras, but it's not true. Like this is not ill-behaved if we want to consider sigma σ-algebras. Yeah.
Boolean sigma algebras are sigma Boolean algebras. Boolean algebras with countable.
Yes. Yes. I don't know why they put the sigma there, honestly, but that's what they decided to go for. But it would be better maybe to call them sigma complete Boolean algebras, if you want to be precise. Yeah. So now we can basically extend the notion of a probability measure. Just we take a sigma σ-algebra and then we say a name valued POVM, and it's going to be a function mu from B to A now instead of C, and we just ask the same assumptions. So that was also the reason why the probability measure was going from B to C, which may have been a little bit weird at the beginning. And now one can show quite easily, okay, that if I take B to be the sigma algebra associated to a certain measurable space Y, and then I take A to be the sigma σ-algebra associated to a measurable space X, then I'm basically rewriting a Markov kernel from X to Y. Okay. As you can see, though, we have changed the direction. So instead of going from X to Y, we're going from Y or sigma Y to the sigma algebra associated to X. So we have like this connection, which is a little bit, which is contrariant in some sense. And now this is like a bit of a recalling that I have characteristic functions, okay, for every measurable set. What maybe can be new for you is that this also generalizes for Boolean sigma algebras or sigma complete Boolean algebras. And now we have a very important theorem here, which is that whenever I have a POVM, then this can be extended to a sigma CPU map. And this really requires us to have sigma σ-algebras. And a sigma CPU map is just a CPU map that preserves the supreme of monotone increasing sequences. And how do you prove this theorem? You Lebesgue integral, just like you reprove the Lebesgue integral. This is at least true for sigma algebras, i.e. the Boolean sigma algebras coming from a measurable space. And then for the general case, you need to find a measurable space associated and then work your way from there. But the idea is basically use the Lebesgue integral. And I really want to stress this theorem cannot be proven if we only consider σ-algebras. So I think this is one of the compelling reasons why considering sigma CPU maps is really important, because now we really have an idea on how to encode POVMs even outside, beyond the finite context. And now I have a question, which was my question about this theorem, is like, can I generalize this to like sigma complete lattices coming from a monotone sigma complete σ-algebra? Like, can I extend then the POVM redefined in the obvious way? And the answer is no, because there are examples of sigma σ-algebras such that A is not going to be isomorphic to the sigma sister algebra with the inverse multiplication, but the projections are still the same. So I cannot expect that to hold. And maybe there is a way to overcome this issue by considering unitary actions, but this was not what we wanted to do. So this is beyond the current presentation. But yeah, there is like there are interesting situations to maybe consider and have like a more deep thought about how to consider unitary actions in general to extend this theorem. And yeah, this is the paper that really allowed me to see why that was not the case. So yeah, thanks, I guess, to the authors. And finally, we have our corollary for Markov kernels. We have measurable spaces and Markov kernels on one side, and commutative sigma sister algebras and sigma CPU maps on the other, and we get a fully faithful functor now. So the adjunction is destroyed immediately, and the problem is that on this side we have things that are pathological, for example, for Neumann algebras, and we cannot get rid of that. So we cannot find a way to go back to measurable spaces and Markov kernels. But this is going to be a fully faithful embedding, which is stronger than what we had before. So, and the reason why is exactly this thing that I was talking about, measurable spaces being isomorphic with their sobriety in this case. Okay. And this nicely restrict to bare measurable spaces and Markov kernels on one side and commutative Peterson bare envelopes on the other, and also for standard well spaces. So we found the theorem we wanted to get all along. It's like a long description. Maybe we can find a better name for that in the future. Unluckily, there has been other definition of what like a standard Borel algebra should be. So we cannot use normal namings that I will use for the commutative side. But we do believe that this could be like a very nice category, and possibly even without the separability condition, this could be a nice category. And now I basically concluded my presentation and just want to give you some remarks and a bit of a refresh of what I covered in this talk. So the first thing is that we do not know how to give a tensor in general for sigma sister algebras. It's really nuanced. We have two notions. It's really hard. But for Peterson bare envelopes, we do have an idea, which is basically have a tensor product on sister algebras and then generalize it to using the adjunction with sister algebras. And this is going to be a symmetric monoidal category whose monoidal unit is initial. So for people working with Markov categories, this is basically the opposite of a semi-Cartesian category. And the last two equivalences are in fact strong monoidal functors, so they respect the tensor product with an isomorphism, and in fact they also preserve the multiplication in the right way. And these were the two remarks that I wanted to say. They should also tell us that possibly Peterson bare envelopes are a good candidate for general quantum probability. Now, key takeaways are, first of all, that we have algebraic descriptions of measurable spaces, which may lead already to some nice works and understanding of measurable spaces that are not really good. Of course, like this part is my project with Tobias Fritz. This other part is all Yuan Chen. Then we also found stronger connections to quantum logic, because now we finally have lattices associated to our sister algebras. Markov kernels are just instances of sigma CPU maps. We can extend Markov kernels to Boolean sigma algebras, basically by looking at sigma sister algebras. And this was novel. And also we have a plausible setting for measurable studies in quantum probability, and also in classical probability, where bare measurable spaces have not been studied as much, although preliminary work is already there. And with this, I thank you for your attention.
Yeah. Thank you.
Yeah.
Are there questions? You're in the audience.
Yeah, like maybe a question. So you mentioned the tensor products. So you get tensor products from the algebra. So which tensor product? For,
Maximal.
Which one?
Maximal. Yeah, I don't know how to move with the minimal. We will need a little bit more, but with the maximal, you can use the universal property and then you extend it.
So maybe another question. So in classical probability, I think so in some like recent works that are trying to do higher order probability. So they have to move beyond Borel spaces and consider things like Borel spaces and things like that.
Oh yeah, okay.
Does your setting generalized that?
I don't think it goes to the direction of quasi-Borel spaces, but what's nice, for example.
Would you get closer or
no, but we do have uncountable Kolmogorov products. And also all states have conditionals. These are very important to us, while quasi-Borel spaces generally do not have conditionals. They're not even positive, right? So.
But I can just make a related question in your previous slides that you had.
Yes. This one?
The other one, sorry.
The other one.
Yeah, with that category, commutative, Peterson, blah, blah, blah.
Uh-huh.
So I guess for reason of you having an equivalence, that category is also not closed with respect to the tensor product.
Which
the category of commutative Peterson bare envelopes, is it closed? Not, right?
Oh, you mean Cartesian closed?
No, closed.
Monoidal closed? No, I think yeah, no.
But this thing that we was mentioning is interesting because there has been this work on the other side on trying to move this category into a higher setting. Perhaps now that you have its equivalence, you can try to borrow their ideas to get a higher quantum setting.
That could be interesting. Yeah, I think there are like two schools of thought. One trying to get Cartesian closure, at least where.
Just monoidal closure in this setting.
Yes, I mean, if I restrict to the deterministic side, right, it should be Cartesian closure. Yeah. So, but in any case, one is trying to achieve this one, and another school of thought is trying to understand conditionals. And I mean, if someone finds a way to have both of this, that would be amazing. But for the moment, it seems they are like excluding each other, as far as I could tell. Although maybe there is more to be said.
With respect to the compact closure that can help in this setting.
Yeah, maybe. Yeah. Yeah, that could be like another idea of considering like other categories for non-commutative probability. I haven't thought about that, honestly.
How do these categories fit in this overview slide that you have?
Right. Basically, now you throw Boolean and σ-algebras out the window. Like in the probabilistic side, this part doesn't appear because you don't know what Markov kernels should be. You kind of infer it from what happens on σ-algebras. This becomes a fully faithful embedding from measurable spaces to commutative σ-algebras, and the other two things are the same. So basically, yeah, like if you restrict to this square, everything works exactly as it is for the deterministic side. which is my focus anyway, like our focus anyway.
Tim, you said something about you have some way of doing Markov kernels with sigma-algebra.
Yes, and the reason is you take the ones described here and you just transpose it using this POVM description, this one. Yes, so you use this thing. But there's been also unpublished work by Sean Moss trying to achieve Markov kernels directly from Boolean sigma-algebras. We discussed that, and he shared some notes, so maybe at some point it will be out, and there should be like a way to describe this same class, but from the perspective of Boolean sigma-algebras, so without considering A here. And it something like involves extending Boolean sigma-algebras to maybe effect algebras, where you have like the unit, and then you kind of tensor, and then kernels are going to be like are going to the tensor product or something like that.
Other questions in the audience? I don't know.
Maybe you want to say something about how conditionals look like here.
Oh, I mean, I just know the description of Markov kernel of Markov categories. We know we have this integration of measures, but the generality for Markov kernels, so conditioning Markov kernels, is still not proven. That would be amazing to see, but at the moment, that is.
In these categories you have
in the category of bare measurable spaces,
yeah,
with Markov kernels, every state can be separated, and you can write an integral. Well, it depends on how. Yeah, you get a regular probability. The thing that in Markov categories you will write like this. Oh. Okay, not this one. This one, okay. You see? Okay, you see, but yeah, okay. So it's just this. Maybe I should give some names. X, Y, X, and Y. It's going to be P, E, and F. Right. So this type of disintegration is allowed. This is how my group writes stuff. This will be basically saying, how can I write this?
So P would be a measure here, and
yes. So P is a measure on X times Y, and then basically this is saying that P of A times B is going to be equal to an integral where I consider just the P, but only like the marginal restricted to X of the map F with the right integration, which is I always struggle with this description. I'm sorry.
That's why string diagrams are so nice. That's why string diagrams
are so nice. Yes. Yeah, no, sorry. At the moment, I don't remember where I should put A and B, but there is a way to write this thing. This is an integral over X, so the element is going to be X. Oh, right, because this is B, knowing B of X, and this is A. Okay. But there is no. Okay, this is better. Okay. So this means that P of A and B can be described by marginalizing P to X and then considering this Markov kernel, which takes X and sends it to B. And this is how conditioning will look like in the infinite case. And for bare measurable spaces, we do have this.
So does it work for kernels as well, or does it work for kernels? So you have a kernel and we can do inversion of kernel.
I don't know. At the moment, we do not know.
What does that give you in the quantum setting?
Yes, there is preliminary work for the finite case, but at least we know that maybe we should look at the journal multiplication more. If you're interested in that, there is this paper by Song and Parzignat, but I don't remember the name at the moment. But it's trying to work out the Bayesian.
So what does it give for the I mean, even in the finite dimensional case, I guess.
Yeah, for
this is like
for a separable state on X and Y, you can show that you have a conditional on one side and on the other side, but the copy is now the Jordan multiplication.
I see. For a separable state.
For a separable state, or even more generally for a PPT state, if you know what that is. I don't remember. But
because so there's some work that try to do at least with finite dimensions to like conditioning on arbitrary states. There's some, well, I think they have sort of competing definition of this stuff by partial outcomes, I guess, and then there it has this like upper and lower conditioning definition for conditional separable and there's I think an older work by like Seconds and Liter or something.
oh yeah, that's
this seems a bit I'm not sure.
Yeah. Okay, that one I know.
Yeah.
And it's more or less the definition that they use here, but that has to be changed and restricted because otherwise it leads to real problems.
It doesn't quite work.
Exactly. But they invented this something like light touch observables. So then if you restrict to that, it should be fine.
They do use the Jordan for some version of that.
Yeah, they basically
they conjugate by the square root.
Yes, there is this thing that they do that and kind of doesn't work. But if you restrict to these special observables, what happens is that you can prove that it's like giving a conditional for the Jordan multiplication. So that's the reason that you consider the Jordan multiplication. It's not that you start with it; it's given to you. Just something nice. And light touch observables are just like self-adjoint elements whose spectrum is 1 and -1, something like this. 1, 0, -1, or I don't remember exactly.
Okay. And the Jordan, use the Jordan. Which kind of, you mentioned at some point you talked about the unitaries and this.
Yes.
Thing. So if you care about the Jordan algorithm, that doesn't clear.
Yeah, maybe. Yeah.
If you want to reconstruct, so this reconstruction of made obviously algebras from the projectors on the projections. So if you only care about the Jordan algebra, then like the thing that's missing that the unitary action is needed is to disintegrate between the different C-star algebras that have the same.
Yeah, that's also what I worry about, and trying to understand exactly which multiplication I should use to think about it categorically. And at the moment, I don't really know. Both? I hope not. But maybe it depends on what you want to do. Any other questions? No? Can imagine that it's been long.
Thank you again.
Thanks. Just before we leave, to announce that next Wednesday there will be another seminar at 3:30 with Rita Gary from Bayern University in Amsterdam. She will talk about, it's a complex title, but it's about the key calculus and some applications. I will send you the abstract, okay, for this seminar. We are all most welcome to come. You conclude it, sir?